We just looked at the turn-based game library. Now let's take a look at the Megamax library, which can take advantage of that. To get started, let's take a look at the negamax algorithm. The negamax algorithm is a search tree that looks forward into the future of a turn-based game to determine how best to make the next move. Essentially, it looks forward into the future, finding the ways to minimize the maximum value that your opponent can take from you. So it's always looking at worst case possibilities. And it does that by looking at a certain number of moves ahead, what it calls plies. So one ply means what's my opponent likely to do given what my possible moves are. And then two plies ahead looks at what am I likely to get after my opponent makes its choice based on what moves I can possibly make. And it goes down that path further and further. And in fact, if you look ahead in this particular game with Mancala, if you look ahead about 8 plies, you have a near unbeatable opponent because it's looking far into the future, far more further than a human can look. That doesn't mean a human can't win. It's just you're not going to be able to do it with just sheer brain power. You're going to have to think of certain strategies that perhaps the Megamax algorithm hasn't taken advantage of. So I'll put some more links down in the doobly-doo covering the Megamax algorithm, including how I used it in the previous game that I wrote. But right now, let's take a look how we're going to use it in this with this nim library. Step one, of course, let's go back to the top of our code here, and we're going to import negamax. And down below, instead of having 2 human players play each other, we're going to go ahead and make one of these players a negamax player. And we need to pass on a depth for a negamax player. This is how many moves into the future, or how many plies it's going to look. Let's go ahead and start off with a depth of 6. So it's going to look 6 half moves, or half turns, or plies into the future. This should do it, except for that I am missing some methods that the AI algorithm requires that we don't have right now. In order for it to look forward into the future, it has to kind of keep copies of state of the game. In other words, if it's going to try a different move, it needs to be able to revert back to the original state of the board. And so we need to add 2 routines that allow for that. One of them being get state and the other one being restore state. So we're going to put that in a moment. And then it needs 1/3 routine, which is called scoring. And this is essentially the tactical evaluation of the board as a whole. For example, if you're doing a tactical measure of chess, you would determine, do I still have my queen or do I not have my queen? Do I still have both my rooks or knights? Do I have control of the center of the board? Is this the mid game or end game? There's a lot of ways you can add strategy and tactics to the game. And what it wants is a number coming back saying, this is better than this. Now, let me back up for a second and talk a little bit more about Negamax's restrictions. Negamax is a variant on a bigger algorithm called Minimax. And the 2 big restrictions it has to be a 2-player game. This will not work with a 3-player game. Secondly, it needs to be a zero-sum game, which means that, for example, in the game of chess, if I lose my knight, that's bad for me, but it's good for my opponent, and vice versa. And for a Negamax to work, everything has to be equally good or bad. So if it's -4 for me, it's +4 for the opponent. Now, that doesn't have to do with like the final score of the game. Like chess doesn't really have a score. You win or you don't, or you go to a stalemate. But what's the relative value of the middle of the game, the tactical or strategic value of that point in the game? And what we need to do is create a scoring method that gives us that answer so the Negamax routine can work. So I'll get back to you in just a moment. Let's put those routines in here. Okay, here we're done. Here's the 3 methods that we've overloaded from the basic game class. Scoring, which returns a float value. And what we're seeing here is I'm pulling something called straight strategic score, which is actually being pulled from here. And all I'm doing right now is a very simple measure. I'm taking the number of stones I have in my store versus subtracting the number of stones that my opponent has and multiplying that by 1,000. So if I have 4 stones and my opponent has 3, that leaves me a net positive of 1, and 1 times 1,000 comes back with a value of 1,000. Now, my final version of this game will actually be much more complicated because I've actually, not to get into another AI, I actually used the genetic algorithm that I wrote in Python to generate much more nuanced scores based on positions of holes and other things in the board. I'm not going to get into that with this video. I'm going to use a simple one here. And of course, that's what's returned here. Now I have, if one person wins versus the other, I have a much bigger value. So the tactical value of me being ahead in stones, I mean, that's not the end game. The end game is to win. And so if it's in a winning condition where one player wins versus another player, it needs to score a much bigger number. So here I have just an arbitrarily big number of 19,000 versus minus 19,000. If someone else won, not me, it's minus 19,000 versus 19,000 for me to win. And I may monkey with this number a bit because I suspect if I have enough stones in the board, I might have tactical moves that exceed the end game value. So I may have to tweak this in a little bit in the future, but that's the idea. You're coming back with a floating point number representing how good the board is at the moment for you. Then we got get state and restore state, and these return strings. Again, because we're using nim, it's very strict about types, and so you can't just return any type that's then returned back to restore the state. So I chose to use a string in the library because strings can pretty much represent anything. You can represent a dictionary using JSON style encoding or numbers or anything. I mean, it's way up. And all I do in this particular case is I take the count of each of the pits and I embed them out to 2 spaces because they'll never be 100 stones in one pit, no matter what you choose for your initial pit counts, stone counts for each pit. So essentially it comes out with a big padded string with those numbers, and then at the very end I store who the current player is, so that later when restore state is called, the correct player is playing and the board is reset back to its proper condition. And so it should be all I have to do is save this and run. Let's try it out. Nim. Let's see. Except I have to import the library. One moment. Okay, it built. These hints about me using scores and that kind of stuff, like I said, I've not implemented all the possible rule combinations. And also I have different ways of scoring the board that I will be eventually putting into the game where I can actually create personalities to some of the AI players. But that's way outside this subject here. Let's run this and see what it does. Let's see, where did I put this thing at? Put it looking 6 moves ahead. It's possible it's going to win. Let's play this game. All right, it's my turn. I'm going to do DC. B's thinking. Oh, it made a move of DEA. So it moved out of here, then out of here, and then out of here. So now it's 3-2. It's slightly ahead, but I'll make up for that. I'm going to do EA. What? Oh, I should have caught that. Oh well. I wasn't paying attention, that's the problem. Anyway, but let's go ahead and finish out this game. Yeah. He won by quite a margin, but... And in fact, I probably could have won this game if I had spent more time and attention on it. I'm doing a video, so I'm not really thinking it through. However, I will say if I set this depth up to 8, I almost never win. So it's a good indicator of how smart the thing is, how far in the future it's taking a look. Anyway, that's the Megamax algorithm library. If you like what you see, please subscribe. Thanks for watching.